missing piece that we haven't had in Pi4All yet is data types, right? You kind of started with data types. Like one of the first things you learned when you were learning Coq probably was, let's define some inductive data types to represent logic, to work with logical propositions, to talk about beautiful numbers. How are we going to do that in Pi4All? So my goal for this lecture is to kind of build up data types piece by piece. So you can see that there's lots of different components that go together when you're thinking about what is a data type definition. And again, I'm going to continue to cheat. I'm not going to talk about the inductive part of inductive data types. I'm not going to care whether this language terminates. There's a huge additional lecture I could give about how to make sure that when you're defining data types and writing inductive or recursive functions over them, you know that they terminate. We're just not going to care about that. I'm not going to do any sort of positivity checks to make sure that your data type declarations are strictly positive. I'm not going to do any sort of checks when we define recursive functions that they terminate. I'm just going to allow us to write anything we like. Now again, we're cheating here, but I want to also give you the impression that it's still, if we are just viewing Pi4All as a language, we're not really giving anything up, right? Or we're not giving up everything. There's a difference. Pi4All, as a dependently typed language, is a type sound language. And we could still, if we wanted to, sit down and prove a type safety theorem for Pi4All, and it can take advantage of the expressiveness that dependent type system offers it. It just loses the ability to have decidable type checking, and it loses that close connection to logic that terminating logics have. Okay, so we're going to talk about data types. And again, I'm not going to, my goal for this is to kind of present the ideas to you without going into all of the details. We're going to work out what the typing rules are going to look like for this version of data types. And I'm going to point out in those typing rules what parts of the implementation correspond to various premises in those rules, right? And so if you're following along, today's lectures, the notes are all in. It's all on the repository on GitHub. Today's lectures are the 4th lecture notes. And if you want to look at the code, I'm going to be referring to functions in the code in the type check file. That's all. Those functions are going to be in the version that has everything, right? So that's the solution version. It has everything that I've worked out for Pi4All. Okay, and I'm going to try to make this a little bit more online by showing you building up data type examples by writing some Pi4All code. So our first goal is we're not going to try to be able to implement all data types all at once, right? So our first step is let's implement data types without parameters, without any sort of constraints, no indices. So what does that mean? It means that we're going to be any data type where you can define it and you give it a name for the type constructor, in this case like nat, and it is directly a type. No arguments, no parameters to these type constructors. What can we do with these? How would we define those? How do we declare a data type? How do we type check them if we see them? How do we type check expressions that pattern match? So for an example, this is some Pi4All code. I'm declaring the data type of natural numbers, and I say it has 2 data constructors, 0 and successor. And notice successor takes an argument. So it's a successor of some natural number, so it has to say what its argument is. And here I have some examples of applying the data constructors to build members of this data structure. And then I have 2 examples here of doing case analysis of this data type. Now the syntax here, I'm kind of inspired by Coq or Agda syntax, but it's fairly similar to what, Haskell or Agda syntax. It's fairly similar to what Coq and ML do, right? So, and here again, for plus, I don't really have any induction principle or recursor for my data type. I'm defining plus just by creating a recursive definition. And I could have screwed it up. I could have defined an infinite loop there. Okay. Just in this category of data types, what kind of data types can I define? Are there data types that I can define? This is not even all of the data types that are in functional programming languages. Like, I can't define list, because list needs a parameter. But are there anything here in Pi for all that I can define that isn't available in like ML or Haskell? Are there any data types that I am getting by virtue of the fact that this is a dependently typed programming language? Yeah. Dependent product. Well, a dependent product is still going to be parameterized because it's going to be a product of two things, and the type needs to say what that product is going to be. But you're right that there's the fact that we have dependency around does give us slightly more expressiveness that even in this restricted version, right? So down here, I just want to show you. So of course, we can have data types. I just wanted to mention we can have data types that don't have any constructors in them, right? So this is a data type void. It has no data constructors. When we do a case analysis of it, we don't have to give it any cases, right? And then here, this is a little bit of a silly example, but it demonstrates that with dependency around, even on these non-parameterized data constructors, we can start to do a little bit of interesting things, right? So this data type, it's kind of isomorphic to bool, right? That's why I called it silly bool, because it's just another Boolean, right? And it has two constructors, I'm true and I'm false. And in I'm true, it takes an argument that's a Boolean, but it also takes a second argument that is a proof that that Boolean is true, right? And remember, we had propositional equality. That's a type. So that means it can be the type of some argument to some data constructor, right? And I'm false. It takes a Boolean and a proof that that Boolean is false. All right, so just to give you a little bit more experience with it, how would we use this data type? And again, it's a silly data type. We're not really going to do anything interesting to it. But let's write a function that takes normal Booleans and constructs members of this data type. How might we do that? All right, lambda b. What would... Gee, how did I end up with that? Right, so what should we do? Yeah.
You can then say,
yeah, if b, then what?
Say, I'm true, b refl.
B refl. Else, I'm false. B refl. Why does that type check? Yeah.
In the context of then, the environment knows that b is equal to true.
Yeah.
I'm true taking the bool in b, and then it tries to resolve b equal to true, and if the environment says b is true, there's a substitution.
Yeah, because of our last lecture where we talked about if, the dependent if, where when we eliminate Booleans, we tell the environment in this branch, type check this branch under the assumption that b is equal to true, right? And that means that refl is actually going to be that proof that b is equal to true is going to be available for refl. Those two types will be, or those two terms will be definitionally equal to each other. And we better try it out. All right, so let me back to Haskell, and we can run the code, right? And you can see, yes, it does type check. Okay, so we can do a little bit. We can have all sorts of, whenever we have a data type declaration, these data constructors, we can have any number of arguments to the data constructors, and those arguments later ones can depend, their types can depend on the values of earlier ones. Just like this type here depends on this value. And there's actually a name for lists of arguments like this. These are called telescopes, right? And where does that name come from? you think about how the scoping behavior works for this list, each variable in the list its scope is the rest of the list. So we have this the sequence of nested scopes that gradually goes out just like a telescope. And that name was invented by de Bruijn. Okay, so we have this telescope of arguments for data constructors, and then we have just basic types. So that's what we want to do first. How are we going to specify how we construct these things? Right? What is our typing rule? We need to say, right, if we have, what does it mean when we have in our code, in our module, we have a data declaration like that? That's kind of like going to the language and adding new constants to it and new typing rules for those constants, right? New constants being new type constants like silly bool, and new data constructor constants like I'm true and I'm false. And we have to say, when do those things make sense? When do they type check? Right? So when we see a declaration like that, it's going to say, well, there's some type constant, and I'll use capital T for a type constant, right? Right? And it's going to be a type. So if in our context, we might have a rule that says, if we have a data type, we're going to remember that there's some type constant in our context. And so that's going to allow us to type check things like silly bool when we see them in code. And what about data constructors? So that's a type constructor. That's a rule that we might use to specify when type constructors make sense. What about I'm true? When are we going to be able to type check some data constructor? So I'm going to call it K. And it may have a whole sequence of expressions as arguments. It's going to have multiple arguments, any number of them. So I'm going to just say A's. Those are all of the arguments. When does that type check? All right, well, again, looking at that data type declaration, we're going to need to have remembered that this data constructor is available. The context, our typing environment, needs to remember that that data constructor is available. So K has to be in our typing context. But what do we need to remember about K? Right? We need to remember that it gives us a T, right? And we also need to remember what its arguments are. We need to remember what its telescope is, right? The telescope that we wrote down right here. So whenever we see this data type declaration, we're going to also extend that context with declarations for all of the data constructors and their telescopes. So I'm going to use D for telescope. Right, D for delta. Right, so we have some K is a data constructor that takes some telescope of arguments. It's going to produce a particular type constant. If we know that's in our environment, well, hopefully the application of that data constructor will give us a T. But there's one other thing we need to check, right? We need to check that all of those A's, they all type check according to the telescope. And so we need to have some sort of auxiliary definition that says when you have a sequence of data constructor arguments, they match up with a particular telescope for a data constructor. So what might that look like? So this is our data con rule. This is our type con rule. What about what would the rule for just this new judgment? So it's a new judgment form for matching up a sequence of arguments against a data constructor, or against a data constructor's telescope. What rules should we need for that? What about 0? Right? It doesn't have any arguments. Right? So it has an empty telescope. So it better make sure that if we have no arguments for, and I'm writing that with just a dot, an empty list of A's, and that should match up with an empty telescope, right? If we were trying to type check 0, it better be that 0 says I don't take any arguments, and we better see that 0 is not applied to any arguments. And that's going to be our base case for this judgment. All right, and then the other case is maybe we have one argument and then we have some more after it. And then we have a telescope that looks like there's a variable and a type and the rest of the telescope, which may have references to that variable. When is that going to make sense? What needs to be true? All right, well, it would better be that that argument has the right type for that argument in the telescope, right? Successor says it takes as a natural number. So its telescope is just nat, right? And so the argument to successor, it had better be an at. All right, and or silly bool, I'm true. Its first argument is a bool, so we better pass in a Boolean as its first argument. And then the second premise for this rule, right, we also need to check that the rest of the arguments for the telescope make sense. Right? So we check all the A's against the rest of the telescope, but that's not right. I see somebody shaking head. Yeah, what else do we need to do? Huh? Both of you know.
So we need to put X into the context.
Huh?
We need to put actually, A or X, I'm confused now, but we need to extend the context.
Okay. Well, so the issue is that D has some free references to X. Or not really free according to Brigitte, but D has some references to X. But we know what X is now, right? We know that X, right, the argument that was going in for X, we know that that's A, the first argument to this data constructor, right? And so we can tell the telescope what that argument is through substitution, right? So we need to substitute in the rest of that telescope. So if you think about how, going back up to here, when we do this application, I'm true, the first argument, if it is true, right, we're going to substitute true for B, and then the second argument would be true arrow true. I mean, true equals true. That would be the type of the second argument, and REFL would work. And indeed, if we had written this instead of B there, we had put true there. That would also type check. Yeah?
This is very similar to the pi rule. Couldn't we just put the constructor with a regular type, a type in the context, and then just use the type checking for that?
Could we have done could we put the, yes, so that's a great question.
What do you put the gains into the constructor?
So we could have taken this data constructor and put a whole bunch of arguments, converted this sort of declaration into a pi type, and not had a special rule for type checking the arguments of the telescope, right? I think we could have done it that way too, but I kind of like this way a little bit better because it talks more about what's going on, right? The data constructor value is not the data constructor by itself. The thing that has that type, its canonical form, does look like a data constructor applied to arguments, and I really like to have a rule that looks like that. Is there another comment? Did you have a comment too? Yeah. I've done it both ways, and right now I don't remember all of the trade-offs and back and forth. But you will often see when you're reading about formalizations of dependently typed languages, especially data type, inductive data types, you're going to see telescopes in a lot of those formalizations. So I wanted to make sure and introduce them to you. You might also see telescopes even in pi types to generalize pi types to take multiple arguments. Okay, so that's how to type check if we see some type constant or we see a data constructor applied to arguments somewhere in the code. That's how some rules that say when it should type check. We can turn it into an algorithm, but it's not too hard. We could probably figure out what direction the information needs to flow, so I'm not really going to go through that now. The other thing we need to talk about is case expressions, right? Because if you remember in our examples, not only do we want to be able to construct these things, but we also want to be able to do some kind of pattern matching. When is a case expression like that well typed? What are the rules for that? So let's talk about type checking a case expression. All right, so we need one more rule for, so this is our judgment for just our normal type checking judgment. And I'm keeping them separate from the telescope judgment. So we have something, it looks like this. Looks like a case expression. In some context, case A of, and then we have a whole bunch of patterns, right? And for right now, I'm just going to sort of write the patterns like this. There's a whole bunch of patterns that are some data constructor applied to some variables that go to some branch for that case. And I'm putting, these i's are intended to be subscripts, right? So there's a whole bunch of, there's potentially many different branches, but they all have the same form of some data constructor applied to some list of variables. That's the pattern for the branch, and then a right-hand side for that pattern. And I'm just going to show you how to type check one of those branches, but we're going to do the same thing for every single one of those. It's a little bit difficult in ASCII to do this list manipulation. Okay, so what do we need to do to type check this case expression in this case? Well, we need to know that, we need to know something about A, right? It should be what? It should be a data type, right? It should have some type that's a type constructor. And then, for each branch, each data constructor for each branch and each pattern had better be in our context, right? So it should have some telescope that gives us a T in the context, right? So for each I, right? And then we want to be able to type check that branch, the AIs, right? So we want to look at AI, every branch, and make sure that they all have the same type, which is the type of the whole case. And you're right, I'm missing something. What am I missing? Yeah, we need to extend the context with the xi's, x's I, right? But what are their types? Yeah, right? Well, actually, di, that, if we assume that the domain of di are the same variables as the x's, then we can just use that telescope as our extension of that context. Because if you look at a telescope, it looks a lot like a context. It's just a sequence of variable declarations, right? Sometimes, like for up here for nat, I didn't put a variable here, but only because it wasn't important to me. I didn't really need that variable, but I could have. I could have said nat is declared this way. That's an equivalent declaration. So every telescope is going to look like a sequence of variable declarations, and that's going to give us exactly what we need to extend the context when we type check all the branches of the case. Anything else for type checking case? Yeah?
You may want to be able to do dependent case analysis.
Dependent case analysis, right. Okay, how are we going to do dependent case analysis?
So we sometimes function like last time, and then
Yeah.
use the case in A.
Okay, yeah, some kind of dependent case analysis, right? So here, just like last time, we had so dependent case, you remember before, we had if, and in the true branch, we assumed that we wanted to say that the true branch could know that the scrutiny was true, false branch should know the scrutiny is false. We want to do the same thing here. All right, so I'm going to specify it in a similar way. So the result type just is going to have some scrutiny in it somewhere, but each branch is going to be able to replace that with something else. And what is it going to be able to replace that with? What does that branch know about the scrutiny? All right, it knows that the scrutiny looks like this, right? Matches that pattern. Right, so it knows that the scrutiny is actually some data constructor applied to those new variables that we just introduced. Right. And that is going to actually, extending the rule in that way is going to give us dependently typed pattern matching. Anything else when we type check a case expression? There's one more thing that we probably should do, but I'm going to really cheat, and because I'm just going to write it like this. We should check to make sure we have enough branches, right? That we cover all the cases of the data type. That we look at all the different ways that we could make a T and we have a branch for all of them. Huh?
Somehow, say we're in doing the algorithmic rules for this.
Yes.
We're in checking mode, and we had information about A that tells us that certain branches are ruled out entirely.
Yes.
The algorithm changes a lot because of that.
Yeah. Right now, there's no way to rule out any branches yet. Right. So right now, the exhaustivity check is pretty easy, but you're right, it's going to get more difficult. And I'm not going to go into the details about how to make it more expressive. But what I've tried to do is give you a picture of building things up incrementally, right, piece by piece. Now, if you go look at the code, where are all these pieces in the code, right? So I just want to give you a quick tour in type check. Right, all of this, if you look at type check, it's a little bit longer now, actually a lot longer now, to have new cases for data constructor creation, right? So we have new, remember our TC term function is, it was our type checking function. It has patterns for all of the different syntactic form. I've added a bunch of new syntactic forms for data types. The one for data constructor applications is this one, decon for data constructor, for some constructor C applied to some arguments. And this is how it works, right? It makes sure that well, we're in checking mode, so we have an annotation. Actually, I'm not going to go through all of this yet because there's still more going on in here than I've explained. But parts of the things you should be looking for are ways of looking up data constructors in the context. So right up here where we say, is this data constructor declared in a context? That's lookup decon. I'll write that over here. Lookup decon. Right? Checking the telescope of arguments against the telescope of the data constructor. Right? That is TC argtella. That's what we're doing right here. And then down here in a case analysis, right, what do we do here? Well, we have to make sure that when we infer the type of the scrutiny, we get a data type. It's something that is a type constructor. So that's ensure tcon. Just like we had ensure pi to make sure that when we had an application, we had a pi type. We're going to make sure that when we eliminate A here, we're only eliminating A if it has the type of a data type. Yeah? Partial application of constructors is not possible. If you want to enable partial application, you'll have to A to expand it, write a function that you can then partially apply. Yeah. Like OCaml, I think. It's like that. Right. And then also going through some of these other parts, this is again looking up the data constructor. That is here where we are taking that, when we are taking that telescope and adding those new variables to the context, that's declare pat. Right? With this part here, the substitution, that's equate with pat. right? And then down here, you can see I even have a function that's called exhaustivity check to make sure that this is exhaustive. Okay, so that's the first step. Simple data types, right? And maybe even not so simple because we have telescopes around. What's the next? Let's extend them a little bit more and make them more expressive. So what else should we be able to do with a data type? What if we want to do list, right? So how does our specification need to change? So we want to be able to do list or maybe or something like this, right? Or and or sigma types. So here's our next goal. What if we wanted to implement data types that look like that? How do our typing rules need to change? Yeah.
I don't see why you can't declare data maybe with your type to type. So do a data declaration that takes the type and returns type.
That's exactly what we're. Oh, why do I name it A?
Yeah, no, I know.
Yeah.
You know, in ACTA,
Yeah.
naming it A that way ensures that all the type is constant in every constructor.
Yes. Yes.
You could just do it where you, okay, I agree to always.
Yeah. So, okay, so what you're bringing up is a lot of times when you see this description of data types, there's a distinction between data type parameters and data type indices, right? And what I want to look at right now are just parameters, right? So what if we want to extend our data type declarations with parameters? And what's the definition of a parameter? What makes it, like we're now saying maybe is a function from types to types, but it's a parameter. That argument is a parameter, not an index. And the reason that it's a parameter, right, is because we give it a name right there, and we ensure that every time we see a maybe, actually, this is not a great example, but every recursive use is also going to be, I should say, everything we're constructing is going to be a maybe A, right? And even our syntax is enforcing that everything we construct is a maybe A, because I'm using this Haskell-style syntax, right? Notice that this syntax, it looks a lot more like Haskell or OCaml than it looks like Coq or Agda. I'm not writing the return type, because I know what the return type is. I know that the return type for every one of these constructors is the same type I wrote above. So nothing and just, they give me a maybe A. Conjunction gives me an and AB. Prod gives me a sigma AB, right? That's the whole point of parameters, is they're not allowed to vary in the return type. They all must be whatever you said they were when you declare the data type constructor. Okay, so the next step is parameters. How do our rules for parameters need to change? All right, let's go back to our rules. All right, so this is the example. This is the example of what I want to do next. How do we need to change some of these rules? Like for checking the applications of type constructors, or even declaring them in the context, right? We need a little bit more information, right? This very first rule there doesn't allow for parameterized data types, right? So what we need is another telescope, right? Because notice that these data type parameters, they can also be dependent on each other. Right down here, if you look at sigma, I have an example of this second parameter. Its type depends on the first parameter. Right? Sometimes you might like that to happen. Right? So sigma is the declaration of a sigma type as a data type declaration. Right? It's a sigma between A and B, but B is allowed to depend on A. So up here in our rules, what needs to happen to our rules? Right? So we need to have another telescope for the parameters of the data type. And then we're going to need some arguments when we see that have to match up with that telescope. And so there was how we're going to get parameterized data types. If we see maybe int, maybe nat, we're going to use that rule to make sure that nat matches with the parameters type for maybe. What about constructing data constructors when we have parameters? Do things need to change? Yeah? Yeah, we need 2 telescopes, right? Right, so we're going to have some B's here that are the parameters of that data type. And what happens to those B's? Well, when we look up K, right, we're going to need to know what the parameters of T are, right? So let's add D prime as an extra. Let me make sure I match the notation. All right. I'll add this first telescope are the parameters of the data type, and I'll even say that I'm going to abuse notation here, and because, well, actually I don't need to do that, right? D prime is the parameter that goes with T. The telescope that goes with T. D is the telescope that goes with K to construct a T that is parameterized by the arguments in D prime. All right, so this D, all the types of the arguments to the data constructors, they're allowed to refer to the parameters of the data type itself. All right, so that's why I write it in this order, D prime before D, because there may be some references in this D to the parameters of the data type. Now, because there are references, that means we need, when we're actually constructing when we're actually constructing one of these members of the data type, we know what those parameters are. And when we look at all of the A's, we don't want to compare just against D, right? We want to actually say, well, we know the parameters are the B's down here from this type. We know it's not just a list of A's that we're working with. You know, cons is constructing not a list of A's, it's constructing a list of ints. And when we type check cons, we don't want to check its second argument against a list of A's. We want to check its second argument. The tail should be a list of ints. And so we need to go substitute those actual parameters for the variables in the type in the telescope D. Right, and again, here I'm again abusing notation to say we can take this list of arguments and substitute it for a telescope inside of another telescope. But that's just another function that we have to write. Unfortunately, Unbound can't automatically generate telescope substitution functions. Yeah? Do we also need to check the B's? That's a good question, right? Should we add an extra premise here that says that that is a good type, right? That will check the B's if we add an extra premise. In the type checker itself, what we're going to do is we're going to make this rule a checking rule, where the T's are where the type is an input to the rule. And it's going to be an invariant of our type checker, of our algorithm, that we're only going to be checking against types that we've already verified are good types. Right? So in our algorithm, we won't actually check the B's, because we get to assume they've already been checked. But you're right, when specifying the system, it's a good idea to make sure that when we say the type of something is, when we say the type of this expression is T applied to B's, that actually is a good type. Okay, so that's construction with parameters. What about case analysis with parameters? Now we have B's here. Now what needs to change? And then we have a D. There's a telescope for the for the data type there that go with the KIs. Anything else needs to change? In which D? This one right here, maybe?
The T.
Or the T?
Yeah. Or releasing the type T,
You mean, so here, when we type check A, we're going to infer its type, and we're going to find out it's some type constant applied to some parameters. Right, so we'll get those parameters from type checking A, and then we'll go to the context. For each of the data constructors, we'll look it up, and we'll see for this particular type T, that T has parameters described by telescope D, and the data constructor has parameters described by DI. Right, and then we want to type check the branch AI. Do we need to do any more substitutions? Is there anywhere these variables could appear? Where could they be? They could only be in the DIs, right, in this rule. Right, so we do have to substitute here, right, to extend our context with the instance of that telescope that goes with this version of the parameters. Right, but that actually is all we need to do, I believe. Somehow I didn't write it down, but I think that is all we need to do. Okay, that's regular data types with parameters. What's the next step? Right? What's an example of a data type we can't do yet? Right? We still can't do everything that Coq can do. Right? What about beautiful? Right? Beautiful doesn't have parameters. Right? If you remember in Coq, let's see here. Right? Beautiful actually has indices. And so there's actually a lot of ways to implement indices. And I'm going to choose the one that's close, that takes the most advantage of the structure that we already have in this implementation. And so I'm going to implement index data types by adding constraints to parameters. Right? So in Coq, you wrote beautiful a little bit differently. Right? Actually, maybe you can remind me what beautiful looked like in Coq. It was something like inductive, if I can spell it. Right, nat, arrow type, prop. Does anybody remember? Yeah, right, B0 just had type beautiful 0. All right, and then B3 had type beautiful 3. Right, so this is the Coq style. And what else? We have 5 was beautiful. And then what was the last one? V sum. And how did you write its type in Coq? Okay, for all n. Beautiful n. Huh? Oh, and m? Like that? Right, then that was the sum of m plus n or something like that? With a period at the end? Maybe some bars? Right, so that's, huh? Yeah. Okay, so this is what it looks like in Coq. This is what I'm arguing is going to be equivalent to that in Pi for all. All right, so this mechanism is going to be a little bit different. but I want to show you how you can get something like indices just by using constraints on parameters, right? So notice that this beautiful, right, it takes a nat to a prop, but the return type of B0, B3, and B5, right, it doesn't return beautiful n. It returns beautiful 0, beautiful 3, beautiful 5. The result type of these constructors varies based on the index to the type constructor. Here, I don't even have the syntax that lets me describe how that works. Right? The result type of B0, B3, B5, Bsum always has to be beautiful n. But what I can do is add some constraints on n. So B0 is going to create a beautiful n, but only when we know that n is 0. Right? And so that's kind of the same thing. Right? If we can only create beautiful n when n is 0, that's the same as saying B0 constructs beautiful 0. Right? And the same is true for B3, B5. So we put these constraints. So I'm in the square brackets here. That's a way of just adding constraints. So constraints is just something else that we can put anywhere in the telescope. Right? We can have a whole bunch of arguments, and in the middle of the arguments, or at the end, or at the beginning, we can have some kind of constraint on them. Right? So that's kind of the connection between the two. And then when we use beautiful,
How is that thing different from putting it in regular parentheses and expecting a proof of this quality?
yeah, that's a great question. What if I had done something like this? Or maybe not even a name, right? Something like that, right? So that would be an argument whose type is a proof of equality, whereas this is a constraint, right? And the difference, it's pretty subtle, right? So when you construct, let's go down and look at how we use this type, right? So here, 3 is beautiful, and so since I'm putting a constraint there, I just want to be able to say B3. If I had made B3 take a proof of equality as its argument, I would have had to say B3 refle, right?
Can't you put any other type into the square brackets with only certain types in a Berlin?
Actually, all you can put is constraints on variables, right? Some variable equals something. Yeah, yeah. It's not a type class constraint. Yeah.
Is the difference that constraint has to be definitional equality?
Mm-hmm.
If you would put it in another parenthesis, it would be the propositional.
Exactly, right. Now, we could have simplified our lives a lot more and just said, well, we already have propositional equality. Just use propositional equalities if you want to implement indices. But it's slightly less convenient for programmers, right? Because when you construct it, you have to give explicit proofs, right, like refle of that propositional equality. And when you destruct it, when you do a case analysis, right, you get an argument that is the proof of the equality, not you get some new assumption in your context that makes those things definitionally equal, right? So works either way, but and the propositional is still available to us. This is just giving us a little bit more convenience. Yeah.
Wouldn't the bigger deal be if you had like another index that was added on the first, and you would want to automatically like substitute in the first constraint into the second index, so that like, you know, if you made like,
Oh, yeah, yeah.
if you made the second index be something like for 0 return unit and put everything else return bool, then you would want to say like n equals 0, like, you know, x equals unit, or unit.
Right, something. So you're saying,
Like make the second constraint a function from nat to set.
okay, nat to set, right? So we need a function from nat to set.
And then like 0 to unit and everything else be like bool.
Not Haskell. Okay, So we have a function from nasta types.
And now beautiful gets an extra parameter that's x of type tn. And then in the data type definition, like data beautiful, n colon nat, and then x colon tn.
Mm-hmm.
And then like for v0, you can say n equals 0, x equals unit. And v3 is like n equals 3, x equals true.
Yeah, yeah.
And with the propositional one, it wouldn't like automatically substitute that.
Let's see if, yeah, so let me just see. Ooh, what am I missing? Oh.
Well, you didn't do v5 or v-sum.
Oh, we don't have to constrain everything. It still should work, right?
Oh, true. Yeah.
Right, I hope so, right? What is it now? Variable true, oh. True. No. Oh, these right here.
You could use this.
We're playing, right? There we go, right? So, and now if we had made it like this, right, then it won't work. Right? So now it doesn't type check, right? It says, in this context where you have a proof that n equals 3, I wanted something that had this t of n type, but instead you gave me something that had type true. Right? Now, we could still make this work, right, by giving a name to the proof, right, and then we could do subst ext by p proof, right, and that would change x's type from t of n to bool, or no, yeah, t of n to bool, I hope. Let's make sure. Oh, that's a constraint. Not arbitrary constraint. But now what is it saying? Expected n equals 3, found bool in context. Now I don't know. Right here? Oh. Huh? Should be t of 3? Huh? Yeah, that's what we needed. Okay, so yeah, so what this dramatically demonstrates, this is how much more convenient it is to have definitional equality than working with propositional equality all of the time. Now, if you were working with an internal language, right, just an internal language of your compiler, maybe you would just make everything propositional equality and just have your compiler work it all out, right? And Haskell's internal language does something very similar to this. But in terms of what programmers want to work with, it's a lot more convenient to have these explicit constraints be automatically applied for us. Okay, so how are we going to implement these guys? Right? Now I should patch it up again so we can think a little bit more about how we use beautiful, because we have to explain not just how to construct beautiful, but also what happens when we destruct beautiful, when we use beautiful in expressions. Right, so this should, right, so we want to be able to construct beautiful. Right, and we also want to be able to look at things that are beautiful. Oh. I don't know if we'll do all of this. Might have fun later. Okay, so how is 8 beautiful? 8 is beautiful because it's the sum of 3 and 5, right? Right, so we want to say B sum what? 3, 5, B3, B5, and that's it. That's all we want to have to write, right? Because we want this definitional equality to be picked up automatically, right? That we want pi for all to prove that 8 is equal to 3 plus 5 after doing this substitution. Now, in Calc, you don't even have to put the 3 and the 5 because it has some type inference there to figure that out from the types of B3 and B5, but we don't have that type inference available to us. Let's make sure we got that. There we go. What about this one? Can we write this one? What is this? Should be very similar to the other one, right? B sum 8. Oh, we also need beautiful n, right? B sum 8 n. 8 is beautiful, and Bn, right? Right. Yeah.
But that would not be
Yeah. You mean like this? Like that?
Yeah, and then we have to specify.
Well, if we leave the type like that, it won't work. Yeah, that definitely won't. That definitely won't work. Why does that work? Well, it's 8. We know what 8 plus n is. Is that it? But then it's plus m1 8 plus n 8. How does it know that n plus 8 is equal to 8 plus n?
Did you save the file topic or audio at the bottom?
It looks like it's saved. Let me. The order is different on the bottom. N 8 Bn 8 is beautiful. Plus 8n. Let's swap this type.
Change the plus n8 to just 8 and see if it likes that too.
Good idea. Let's make sure the type checker is just not the completely agreeable type checker, which is everybody's favorite. Aww. There must be. Okay, clearly there's a bug.
Are the errors coming the bottom?
Huh? No. It's clearly a bug. Homework. Missed something. Okay. How do we implement this?
But why don't you work when you swap it around?
Huh?
Why shouldn't it work?
Oh, why shouldn't it work if we swap it around? It doesn't work in Calc either, but yeah.
Right. It's not obvious that n plus 8 is
Then that requires that you know that the operator plus is associated, which is not something that we know and take for granted. But
How do we implement these indices, right? Right. Well, we need to represent them in our telescope first, right? When we have a telescope, like up here, we need to be able to have, as well as assumptions about variables, these arguments to these data constructors, we also need to be able to put these constraints in our telescope, right? And what that means is all of our operations that work on telescopes also have to work with these constraints. So here, when we are type checking lists of variables against a telescope, we're going to need another case when the head of our telescope, instead of being an assumption about an argument, is actually some kind of constraint, x equals a, right? In which case, we're not going to actually consume any arguments from our list of constraints. We're just going to make sure that our definitional equality is satisfying that constraint. Right? When we construct B sum, right, and we're adding things together, we have that constraint at the end. We need to make sure that that constraint holds. We want to make sure that definitionally, not A equals A, X equals A. Whatever we set our constraint, whatever constraint we put on that parameter, it actually is true. Right, so that's one thing that we have to do when we're checking these arguments to data constructors. Another thing that we have to do is remember that we have to do a lot of substitution through telescopes. Right? Here's substituting one telescope through another, a list of arguments through it, or just a single substitution right here, a term for a variable in a telescope. What if we're substituting for a variable that we have a constraint for? Then we need to figure out how to resolve that substitution. Right? Maybe that substitution is going to give us a constraint, is going to give us new constraints. Right? We're going to have a term on one side. You know, it's going to be, our constraint might say 3 equals 3. It might be a trivial constraint. It might be an unsatisfiable constraint, 5 equals 3. Or it might be that we have, you know, just X equals just Y. And we might want to refine that constraint to X equals Y. Right? Or it might be a substitution that we can't really do anything with. F of X equals 3. We can't really resolve that into a constraint on a variable that we can use. And those, maybe we have to figure out what we're going to do with. That might be where our bug is. Right? And so all of that is bookkeeping, but it's keeping track of this information that when we have data types like that, it's not working for any natural number, but only certain ones. Okay, homework. Of course, find the bug. I also have homework for you that is playing around with programming in Py4All and having fun with this stuff. So if you go look at the file logic.py, right, you'll see it looks a lot like the software foundations section of logic. I basically took the Coq code and tried to translate it to Py4All. But I put some trust me's in there. And so your job, if you want to, is play around with it. This will give you some practice, but don't just fill it in and make it work. Also think about, why does it type check? Why is it telling me that it's okay, that this works, that this is the right expression to fill in the blank here? Unlike in Coq, where you're using tactics to show that and commutes. Here you have to actually write out the proof term that and commutes. We'll get to these square brackets in just a minute. So logic, this is only for parameterized data types. If you want to also play around with index data types, I have another file called fin1.py, and it takes some parts from the AGDA standard library for finite numbers. So this is an example of dependent data type. Right? So fin is indexed by a natural number. So when we have the type fin0, that doesn't have any elements. That's the empty set of numbers. Fin1 just has one member in it. There's only one element in fin1. It's called 0. Fin2 has two things in it. It has 0 and successor of 0, and so on. Right? So if you want to say, I have a finite set of numbers and it's bounded, it's between 0 and this number, that's fin(n). And in this file, I define fin using constraints, and then I also ask you to fill in some of these blanks to play around with index data types in Py4All. Okay. That's homework for data types. Now back to those square brackets here. Why did I write some of these things in square brackets? There's one last topic that I want to talk about, and I don't really have a lot of time, but it's still an important topic. And that is erasure, i.e., when we're representing data structures, what components of those data structures do we really need to have around at runtime? Which ones are important for computation, and which ones are only there just to make our code type check, right? For example, in Calc makes this distinction between prop and set. Things that are in prop are not computational. They're part of the proofs about your program. Things that are in set, if you were to take your Calc development and extract it into something you could run, only the things that are in set would stick around, because only the things that are in set are the meaningful parts of your program. Pi for all, I wanted to show you a different way of distinguishing between things that you need at runtime and things that you need at compile time. And so what I'm showing you here is the ability to have erasable arguments, both in your data type definitions and also having functions that take arguments that are erasable, right? So if you look at proj1, so this is proj1 is an example of a function that takes two arguments that are erasable, right? The types A and B, right? To take an and, a conjunction, and return the first component of it. All we really care about, all what's important is P, right? This argument here. We don't actually have to look at what the type is of A or what the type of B is. They're kind of like type arguments to this function. And just like Haskell or ML could erase types before we run it, in Pi for all, we don't need these types either. And so I'm marking them with square brackets to tell Pi for all we could erase these types. Now, I don't have an implementation that actually does that erasure. We don't have the type checker. We don't have any more of the compilation. But the next step in the compilation here would be to erase anything that's in square brackets. Right? And then when I create the lambda expression for proj1, I'm also marking these two arguments as erasable arguments. That's why they are in square brackets. Yes?
The type checker, though, I think, flags arguments that are not supposed to be erased.
Yes, that's important, right? We want to make sure that if we say something is erasable, it actually is erasable. All right, so let's try to screw that up. And let's see if that works. Right, so down here, right, so say we are writing a function. Actually, I think I have this worked out already. The identity function, its type is erasable. But down here, here's a incorrect version of the identity function. It says, right, it takes in a type it claims is erasable, and then it takes in a second argument of the type of the first argument, and it claims that second argument is also erasable, but then it returns it. All right, should this work? Can we get rid of y? Do we need y at runtime? Yeah, we're returning it. Where does it come from? It's the result of this function. Right, so this should give us a type error. Right, so this is in lec4.py, demonstrating these erasable arguments. Right, and there we do. We have a type error. Let's read the type error. Right, that says, erased variable y is used in the body. Okay, so how does the type checker know that this is wrong? Well, we said we were going to erase it, and we used it. So what does it mean to use a variable? What counts as a use? Am I not allowed to put y anywhere, or what do you think counts?
Sort of naively, anything on the right-hand side. If it appears on the right-hand side of the equation.
Yeah, if it appears, okay.
But if it's used in a place that we're going to erase, then
Yeah, it's not so simple, right? Right, because here's an example where I use it on the right-hand side. Is that okay? Right, I used it in a type annotation. Right, that should be fine, right? Right, so that works. All right, so it can't just, so it's not just, is this variable free in this expression? That's not right. All right? Huh? Oh, well, that's y, but x also appears. Right? And what about this? All right, so here's ID, which is defined up here. It has its first argument is erasable, second one is not. It's actually very similar to ID prime. Is this x, is that a use or not? All right, that should be fine. All right, passing something that's erasable to something else that expects an erasable argument, that should also be fine. What about if we had a data structure, right? Let's see. And here is an extension of data types with erasable arguments. Right? Now that declaration, hopefully I got the syntax right, of, not colon, right? With that guy, now we can start using it, right? Make x y, and now ID prime prime should have type a lot like that type, except returns a t. Is that still going to work? Is that a use of x? I've stuck it into a data structure. But I said the data structure had some erasable arguments. That should still be fine. Okay? What if I pattern match on a data structure with an erasable argument? Right? I should be able to pattern match it because I might want to use it in a type annotation or pass it as an erasable argument somewhere. I just can't use it by itself. That should also be fine. So when we stick it into a data structure, we're promising we're always going to, when we pattern match on it, we're always going to use it in an erasable context. Why does that make sense? Because when we compile this data structure right here, we're not going to allocate any space for this guy. We're going to erase that. Right? And now, this is all very abstract. It turns out that it's really useful to have erasable arguments. Sometimes you can say that certain parts of data structures are erasable, like vectors are length index lists, right? And in AGDA or in Coq, right here we're going to say vector A, that's the type of all the values stored in the vector. N is the length of the vector. We can make that length not stored with this data structure by making it an erasable argument to cons. Otherwise, we're going to have cons 1, or cons 0, cons 1, cons 2, cons 3, cons 4. We don't need to store all of those indices. They're only there for type checking. Right? And then we can think about what does that mean when we're writing programs with this definition of vector? Can we still write everything? Right? We could, for example, here is a version of append. Right? We're checking that the lengths match up, but we don't need to know what those lengths are at runtime. So your last bit of homework, right? And actually, I'll write it up on the board so that we remember everything. Right? So one bit of homework was to look at test logic, right, which gives you some practice with parameterized data types. It also has some erasable arguments there to give you some practice with that. The next bit of homework, test fin1.py. that gives you some practice with a parameterized data type. Once you get that done, your additional part is to go and think about if there are any parts of that that can be made erasable in that fin data structure. Do you need to have all the components in the definition of fin, or can you erase them? Can you go through that file and add square brackets to make it so that less of that information is needed at runtime, to tell the compiler which you need and which you don't? Right, so finish the trust me's, right, add erasure. Right, and so that should give you a little bit of experience. Now, how we implement that, right, for data types we have to tag the arguments for whether they're erasable or not. Whenever we introduce something into the context, like when we have a lambda expression that takes an erasable argument, when we type check it against this new erasable pi type, we need to make sure that argument's not used. And to define what a use is and what what isn't a use, that's in syntax. In the syntax file, there's an extra function that's called erase. That what it does is it removes all of the type annotations and all of the erasable arguments from the term, and then we just run the free variable function on that. Right, and that will tell you all of the free variables left after we've done that erasure are the ones that are actually necessary for doing that, for necessary at runtime for that term. Okay, so that's it. That's everything I have to show you in Pi4All. Of course, it's a demo language. There's much more that you could add to it. You could think about how to make it a terminating language, how to enforce termination in this language. You could think about how to enforce termination for certain parts of this language. You could think about type inference in this language. How do we use unification so that we don't have to write down so much information, right? Because as you notice, Pi4All terms, if you do the homework, they're a little bit, they're going to be longer than certainly Coq tactics. They're also going to be longer than AGDA terms, right? Or you can think about how you might develop this kind of, what tools might be useful for programmers who are programming in Pi4All. Ulf, when he gives his lectures on AGDA, you'll see that he works very closely with the Emacs mode of AGDA to help him interactively developing the code. I think that's a really important area of research that hasn't gotten enough attention. How do we write this code in the first place? What tools can be useful for programmers and developers or people who are trying to prove things in proof assistance? And I think that's about it. So, code is yours. Have fun with it, and thank you guys so much.